Hi everyone, I am Anantalakshmi. I am the IIT Madras ETDCS expert faculty. Yes, this is from the chapter Solid State, which is the very first chapter in 12th standard syllabus. Okay, so let's read the question. The cubic unit cell structure of a compound containing cation and anion is shown. The cation has a smaller ionic radius. Okay, now we have to find the correct statement. Okay, so you should know M is the cation and X is the anion, right? Because cation has smaller radius. Yeah. Now, as you can see, now you have to find the formula based on the contribution and the places. Okay. So we can see this cation, it is located at the phase centers. Okay. FC, I will say phase centers, two phase centers. So contribution will be half for each phase center atom, which the effective contribution will be 1. Now, this anion are at the edge centers, EC, and each edge center contributes 1 by 4th into a cell, into a unit cell. So there are 4 atoms in total, and the contribution of each edge center atom will be 1 by 4th, which gives 1. So the formula we can say mx. Okay, contribution is 1 for each. So this is correct. Empirical formula of the compound is mx perfect. Now, cation M and anion X have different coordination geometries. That is wrong. Because here, see, M is surrounded by 1, 2, 3, 4, and here also there will be atoms 1, 2, 3, 4. So basically, it is surrounded by 8 neighboring atoms. And if you kind of see, what about this? The surrounding atoms, if you visualize the surrounding atoms for cation and anion is the same. So there is no way they can have different coordination geometry. They will have the same coordination geometry. So this is wrong. Okay. Now, this we have to calculate. We have to find the ratio of the mx bond length. Okay, that we have to find. So mx bond length. Okay, we need a little bit of a visualization here. Let's say this is the mx. I'll use a different color, maybe. Okay. Oh, why don't I have the option? Oh yeah, I have. Yes. So if we take this, okay, the centers joining this, I mean, joining the center of this anion and cation. So if you see, this is basically the body diagonal of the chota cube. Okay, chota as in the cube of size a by 2. Sorry, a by 2. That is a by 2. So basically, what is the body diagonal? Root 3 a by 2, right? Body diagonal is given by root 3 a by 2. Now we can approximate it as the distance between the centers of these two, which means the bond length. So root 3 a by 2 will be our bond length, okay, which is mx bond length. And they're asking the bond length ratio to edge. Yeah, that means mx by a. When you divide it both sides, mx by a will be root 3 by 2. And we can easily say that root 3 by 2 is 0.866. So this is correct. Okay, I'll change the color. Okay, now the next option, the ratio of the ionic radii of cation to anion is 0.414. This we can't really comment because from the shown diagram, we can't say which kind of fittings it is. We should really know, I mean, we need more information to comment on what is the closeness or the packing fit between atoms. So we can't comment anything. So we can't comment anything about B. So we'll just leave it. We can't really say give a value for that. So the answer will be A and C. Great. Now moving on. Okay, this is a titration question. I'll read it. 5 ml 0.1 molar oxalic acid solution taken in a conical flask is titrated against NaOH from a burette using phenolphthalein indicator. This is something we do in labs actually. Uh, Basically, there is this thing called pipette and burette. Okay, burette is something like this, and you will have a conical. Oh, sorry, it doesn't look like conical. Yeah, conical flask, and then you loosen it so that NaOH will drip. So here there is NaOH, and here we have this acid, which is oxalic acid. Okay, so here we have acid. What they're asking is the volume of NaOH required for the appearance of permanent faint pink color solution, which means for neutralization. Okay. Yes. So what is given is 5 ml 0.1. Oh, I can't write point. Yeah, 0.1 molar. Yes. So this is given. And now we have to see the volume of NaOH required for neutralization into molarity of NaOH. Okay. But we can actually equalize the millimoles. But instead, we have to equate the milli equivalence. We have to equate it into the number of equivalents. For NaOH, it's 1. But for oxalic acid, for each millimoles, you will get 2H plus. So the equivalent will be multiplied by 2. So 2 into. Okay. So this is 2 into 5 into 0.1 milli equivalents, which is 1 milli equivalent, which would be equal to V into M, molarity of NaOH into 1. Because NaOH there is only one OH minus, one equivalent OH minus. Okay. Great. This is from the very first chapter, Basic Concepts of Chemistry. Now we have to find the volume, okay, of the NaOH. That is why we need the use of this table. Yes, this is the little bit tricky part. So usually we actually think that when we see this, we have to take the average of all the values, but that is absolutely wrong. Okay, so what should we do? Normally we take the average of all these readings, and then that is not right. This is why we have to observe. Here we can see they're repeatedly giving 9 ml, right? 9 ml of NaOH. So we shouldn't take average. We should assume that this is pilot reading. Because of the initial, the friction, that friction caused by this burette tightener, that is why it became a little more. But when you use it a lot of time, when you use it repeatedly, that friction reduces and you can instantly stop the tightener of the what is it, burette. Yeah. So when you get a constant, when they give you a constant values, if you can identify that the volume is constant as you keep on taking the readings, then that value only you should take. So what I'm saying is that you have to take volume of NaOH as 9 ml here. Okay, sorry, this is 9 ml. Okay, if you take that, then you can definitely find out the molarity of NaOH. Molarity will be 1 by 9, which is 0.111 molar. So that is the answer, 0.111 molar. Yeah, this was a numerical question, kind. I think this is clear for you all. Let's go to next question. Okay. Okay, this question is this question is a hybrid of equilibrium and thermodynamics. Let's read this carefully first. Consider the reaction A giving B, giving B and back at 1000 Kelvin. Okay. So at first our temperature is 1000 Kelvin. Okay. And at time t dash, the temperature of the system was increased, okay, to 2000 Kelvin. Fine. And the system was allowed to reach equilibrium. Great. Throughout this experiment, the partial pressure of A, okay, the partial pressure of A is constant and is given as 1 bar. Okay. So A will be always 1 bar in both the cases. okay, for 1000 and 2000. I mean, the pressure of air is maintained. So, okay, what we are given is the partial pressure of B. We are not directly given, but we are given this graph where in y-axis we have the partial pressure of B as a function of time. Great. So we are asked to find the ratio of standard Gibbs free energy at 1000 and to 2000. Okay. So basically we have to find delta G at T1, which is 1000 divided by delta G at T2. That is what we are asked to find. Okay. So this is basically kind of easy because first we just have to find the partial pressure of B from this. So here, as we can see, before time t, it is at equilibrium, and the equilibrium partial pressure of B is 10 bar. Okay, see 10 bar, and after after increasing the temperature to 2000 Kelvin, and it is allowed to reach equilibrium, then the partial pressure of B is 100. Okay, so this is pretty observational. We can say 10 bar will be the final pressure of B, and 100 bar will be the final. Sorry, 10 bar is the final pressure of B when equilibrium pressure of B when temperature is 1000, and 100 bar will be when the temperature is 2000. So we just have to find the standard Gibbs free energy. We know the formula of standard Gibbs free energy from thermodynamics chapter as minus RT ln K. So for one, it is RT ln K1, KP1. Okay, minus RT2 ln KP2. Okay, so R cancels. We have to find what is KP1 and KP2. First of all, KP1 will be what? Both are gases, right? Yes. So partial pressure of product by partial pressure of reactant, which is 10. So KP1 is 10 and KP2 will be 100 by 100. Okay, right. Now we can just put it in the equation. Okay. So the ratio will be T1. What is T1? 1000, right? 1000 into ln 10 divided by 2000 into ln 100. Yeah, great. So 1000 into ln 10 by 2000 into ln 100. We know 10 square is, yeah, so when we calculate 2 ln 10, 2 ln 10, so 1000. So answer is 1 by 4.25. So that's pretty easy question. You just need to, it's kind of formula based because we have to know the formula of delta G, which is minus RTL and KP, and we need to know what is KP, and we need to find the data for B from the graph, and pretty much it's done. This question is done. Okay, let's move on.